So here we want to use the fundamental theorem of calculus to find the following derivative. We have the derivative with respect to x, or ddx, of the definite integral from 0 to e to the power of 2x of the natural log of t plus 1, and we're integrating with respect to t. Okay, and so first off, let's just do a quick refresher on the fundamental theorem of calculus. In particular, we're going to focus on the second part of the fundamental theorem of calculus, which looks like this. We know that the derivative with respect to x of an integral from some constant a to x of a function f of t dt is equal to f of x. All right, this is the definition of what we usually refer to as the second part of the fundamental theorem of calculus. If you're taking the derivative of a definite integral from a constant to x of a function in terms of t that is being integrated with respect to t, the result is that function but evaluated at x. Now, that's how it works when that upper bound is just the function of x. But if you take a look at our derivative here, we have the integral from 0 to e to the power of 2x. And so that's not just x. So our derivative here is probably not going to just be f of x. It's probably going to look a little bit different. And I think you'll see where that's going to come into play as we work on taking this derivative. But to get started here, to use the fundamental theorem of calculus, what we should do is set the integrand, or the function inside our integral, this function in terms of t, the natural log of t plus 1, we should let that be f of t. Set that equal to our function in terms of t. All right, so this part right here, I'm going to let f of t equal the natural log of t plus 1. All right, so now what we can do is rewrite this expression. It's going to be equal to the derivative with respect to x of the integral from 0 to e to the power of 2x. And now we're going to have f of t, or our function in terms of t, times dt. All right, and so now the next step here is to integrate this function in terms of t, and we're just going to represent that with its antiderivative, right? For a function f of x, we say that the antiderivative is capital F of x, or in other words, for a function capital F of x, small f of x is the derivative. All right, so if this is the derivative of this function, then this is the antiderivative of this function. We're going to say that the integral of a function f of t would be its antiderivative capital F of t. All right, and then we're going to evaluate that from 0 to e to the power of 2x. So what we'll have here is that this is equal to the derivative with respect to x of the antiderivative capital F of t, that is the integral, or the antiderivative, of f of t, but now it's going to be evaluated from 0 to e to the power of 2x. Okay? Now, what we can do is evaluate this antiderivative at e to the power of 2x and subtract the evaluation at 0. That's using the first part of the fundamental theorem of calculus, which, if you boil it down, just tells you how to evaluate a definite integral, which is what we are doing right now. And so let's work on that here. This will be equal to the derivative with respect to x of capital F of e to the power of 2x. So we'll have e to the power of 2x. And then we're subtracting capital F of 0. All right, so we have capital F of 0. Now, what we can do next is take the derivative of these two terms, right? This is the result of evaluating this integral, or integrating this function f of t, and then evaluating it at the bounds of integration. And so now we can just take the derivative with respect to x of these two resulting terms. And so this is where things can get a little bit tricky. Let's continue our work up here. If we take the derivative of capital F of e to the power of 2x, what is going to happen here? What do we have right here? Well, what we have here is a composite function, or in other words, a function inside another function, right? We have e to the power of 2x, a function, inside the antiderivative capital F. So when we take the derivative of this term, or of this composite function, we have to use the chain rule, which allows us to take the derivative of composite functions. We take the derivative of the outside function, keeping the same inside function, and then we multiply by the derivative of the inside function. So here's what that will look like. We need to first take the derivative of the outside function, which is the function capital F, and remember that this is the antiderivative of small f, which means that the derivative of the antiderivative is small f. All right, we sort of touched on that earlier. So the derivative of the outside function is small f of that same inside function. So we still have e to the power of 2x on the inside, but then we want to multiply by the derivative of that inside function. And so we need to take the derivative of e to the power of 2x. And what is the derivative of e to the power of 2x? Well, we actually have another composite function here. The outside function is e to the power of x, but then the inside function is 2x, right? 2x is plugged in for that power of x. So really, we have to use the chain rule again for the derivative of this inside function. We'll start by taking the derivative of the outside function, and the derivative of e to the power of x is just itself. So we're going to end up with e to the power of that same inside function, but then we want to multiply by the derivative of the inside function. Or in other words, we're multiplying by the derivative of 2x, which if you use the power rule for derivatives, is just going to give you 2. Whenever you have x to the first power, the derivative is just equal to its coefficient. So we're multiplying by 2. Okay, so that's the full derivative of capital F of e to the power of 2x. We used the chain rule twice to take that derivative. The derivative of capital F is small f, and then the derivative of the inside function e to the power of 2x is e to the power of 2x times 2. Now we're not quite done yet with our derivative. We still have to take the derivative of capital F of 0. But what really is that value right there? Well, it's just a constant, right? If you're evaluating a function at a constant value such as 0, the result of that would just be a constant. And so if you're taking the derivative of a constant, the derivative is always 0. All right, so that's just going to become 0. So we'll have minus 0, and we don't really have to worry about that. That's not going to change our answer. So let's simplify what we have here. This will be equal to 2 times e to the power of 2x times small f of e to the power of 2x. Okay, I just reordered the multiplication here to make it look a little bit nicer. And now we're almost done. We have one more thing to do to finalize our answer, and that is to replace our function small f with what we set it equal to. Right? Remember that we let small f of t equal the natural log of t plus 1, that function that was inside our original integral? So, to rewrite our final answer here, we should rewrite this part using that function, the natural log of t plus 1. We are plugging e to the power of 2x into small f of t, so we're going to replace that t in this natural log function with e to the power of 2x. All right, that's all that's going on here. We're plugging e to the power of 2x into small f of t. So let's write it out. This will be equal to 2 times e to the power of 2x times the natural log of t plus 1, but t is going to be replaced with e to the power of 2x. So we have e to the power of 2x plus 1. And that right there is our final answer. That is the derivative of this expression, or this integral, using the fundamental theorem of calculus. And so as you can see, our answer is a little bit different than what you might expect based on the definition of the fundamental theorem of calculus that we looked at earlier. And that should make sense because remember that in the definition, we just had the integral from a constant to x, not e to the power of 2x like we had in this case. So our answer is not just this function evaluated at e to the power of 2x, we also have it multiplied by the derivative of e to the power of 2x. All right, and that's what's going to happen when you have an upper bound in a problem like this that isn't just x. If it's some other function, you're going to end up having an answer of the function inside the integral evaluated at that function, but then multiplied by its derivative. And technically that is still true if the upper bound is x, because the derivative of x is 1, so you'd have the function evaluated at x, but then multiplied by 1, which doesn't change anything. Okay, so I hope that makes sense. That's sort of the thought process behind how the fundamental theorem of calculus works for this type of example. If you have any questions, feel free to let me know in the comments. And if you want to learn more about the fundamental theorem of calculus, I do have some more videos in my Calculus 1 playlist that you can check out, so feel free to look into that. But if you don't have any questions, this is all I had for this video, so I will see you next time.